Hello, good morning, sir. Good morning, everyone. Today we're going to solve the system of linear equation using different iterative techniques. So today our focus will be on the numerical solutions of system of linear equations using the Jacobi method and the Gauss-Siedel method. So our aim for this is to solve the following system of 4 linear equation with 4 variables and determine the values of x, y, z, and w that concurrently satisfy all equations within the system. However, before proceeding, we must check first if these two methods or if these two iterative techniques is applicable to our system of linear equation. And that would be by solving or by looking at its diagonal, or also called as diagonal dominance. Now that we have our coefficient matrix, we are going to check for its principal diagonal, and that would be right here. Now, let us evaluate the diagonal dominance of our matrix. A matrix is strictly diagonally dominant if for every column, the absolute value of the diagonal element is greater than the sum of the absolute values of the off-diagonal elements in that column. So that would be if the absolute values of our elements in the principal diagonal is greater than the summation of also the absolute values of the elements in our non-principal diagonal. So for the first column, that would be if the value of our principal diagonal here is greater than the value of our non-principal diagonal elements. So to check, it should be the absolute value of 10 should be greater than the absolute values of our elements here. So that would be 1 plus 2 plus 0. And since this is correct, 10 is greater than 3. Then for our second column, that would be 11 is greater than 3 plus 1 plus 1. That would be 11 is greater than 5, and that is correct. For our third column, that would be 10 is greater than 2 plus 1 plus 1. So that is 4. 10 is indeed greater than 4. And for our last column, it should be 8 is greater than 3 plus 1, and that would be 4. And this is indeed correct. So this means that we can apply these two methods to solve for its roots. Now, to implement these iterative methods, we must first express each variable as a function of the others from its respective equation. So this would be our equation 1. And this would be in terms of the value x. And in order to do that, we're going to transpose the non-x values to the right side and divide this with 10 in order to cancel x. This would be our equation 1. This would be our equation 2. However, this would be in terms of y. This would be an equation 3 in terms of z. And this would be our equation 4 in terms of w. Now, that would result to this equation that we have right here. So for x, again, I just transposed the non-x values to the right side. So that would be 10x is equals to 6 plus y minus 2z, and then divided with 10 in order to cancel the 10 here. For y, that would be 11y, and then transpose all the non-y values. That would be 11y equals 25 plus x plus z minus 3w, and then divide it with 11 to cancel the 11. For z, that would be 10z is equals to negative 11 minus 2x plus y plus w all over 10 to cancel the 10 that we have right here. And for w, that would be 8w equals 15 minus 3y plus z divided with 8 to cancel the 8. Now next, for our initial approximation, we are going to employ the zero vector, wherein the values of our x, y, z, and w would be 0. This would be 0, 0, 0, 0. And then we are going to solve for the values here for x sub n plus 1, y sub n plus 1, z sub n plus 1, and w sub n plus 1 using our equations that we have here above. Now for x sub n plus 1, we're going to use the first equation, which is in terms of x, and simply plug in the values of y and z, and that would be 0 and 0. Then for y sub n plus 1, we would use the second equation, and again plug the values of x and z and w, which is 0, 0, 0, 0. The same goes with z and our w right here. Now let's solve for our first iteration. Our x sub n plus 1 would be 6 plus 0, since y is 0, minus 2 times 0 all over 10, and that would give us 0.6. For y sub n plus 1, that would be 25 plus 0 plus 0 minus 3 times 0 all over 11, and that would be approximately 2.2727. For z sub n plus 1, that would be negative 11 minus 2 times 0 plus 0 plus 0 all over 10, and that would be negative 1.1. Now lastly, for our w sub n plus 1, that would be 15 minus 3 times 0 plus 0 all over 8. That would give us 1.875. Now, with the values that we solved right here, we're going to place that in our table here. So that would be 0.6, 2.2727, negative 1.1, and 1.8750. Now, for the second iteration, we now utilize the values from our first iteration, the values that we got right here, to compute for the values for our second iteration. So, the values that we solve right here would be our initial values again for the second iteration. Now, we're going to do the same again. So, for our second iteration, we're just going to plug in the new initial values, which we have right here, for x, y, z, and w to our equation right here. So instead of 0, x would be 0.6. So this would be 6 plus the value of y, which is 2.2727, minus 2 times the value of z, which would be negative 1.1 all over 10, and that would give us 1.0473. Next, for our y sub n plus 1, that would be 25 plus the value of x plus the value of our z minus 3 times the value of our w, which is 1.875 all over 11, and that would give us 1.7159. Next, let's solve for z sub n plus 1. That would be negative 11 minus 2 times the value of our x plus the value of our y plus the value of our w all over 10, which would give us negative 0.8052. Lastly, for w sub n plus 1, that would be 15 minus 3 times the value of y, which is 2.2727, plus the value of our z all over 8, which would give us 0.8852. Now we're just going to write that in our table here. And again, we're going to iterate again and use again the same values for x, y, z, and w as our initial values for x, y, z, and w right here. So we're going to iterate again and again until the value of our x sub n and our x sub n plus 1 is equal with each other. So that would be our x sub n is equal with our x sub n plus 1. Our y sub n is equal with our y sub n plus 1. Our z sub n is equal with our z sub n plus 1. And our w sub n is equal with our w sub n plus 1. So you're going to iterate again and again until they are equal with one another. Now to do that, let's use Excel to make it faster. So as you can see, we have the table right here. So our initial values for x, y, z, and w would be 0. For our column right here, we're just going to simply plug our formula. That would be for x, that would be 6 plus y, which is this one, minus 2 times z, which is this one. Close parenthesis over 10. Next, for y, that would be 25 plus our x plus our z minus 3 times w all over 11. For our z, that would be negative 11 minus 2 times our x plus y plus w all over 10. Lastly, for our w, that would be 15 minus 3 times our y plus our z all over 8. So next, as what I said, the values of our x sub n, y sub n, z sub n, and w sub n would be the value from our x sub n plus 1, y sub n plus 1, z sub n plus 1, and w sub n plus 1. So x sub n would be equal to this one. Y sub n would be equal to this one. Z sub n would be equal to this one. And w sub n would be equal to this one. Next, we're just going to drag the formula down and see when our values will be equal to one another. So next, we're going to drag this down to apply the formula or to apply the same formula below. Let's also drag this down, and drag this down. The same goes for here. So this right here, where our values of our x sub n and x sub n plus 1 is equal with one another. As you can see, 1 is equal to 1. And for our y, 2 is equal to 2. For our z, negative 1 is equal to negative 1. And for our w, 1 is equal to 1. Now, this would be the root of our linear equation. So the value of our x is equal to 1. Y is equal to 2. Z is equal to negative 1. And W is equal to 1. That is for Jacobi's method. However, for Gauss-Siedel's method, it's also quite similar with Jacobi's method. And in fact, it is also shorter. Now, how are they different with one another? So for Gauss-Siedel's method, this method distinguishes itself from Jacobi by immediately utilizing the most recently computed component values within the same iteration. So the same formula will be applied. However, the values of our x, y, z, and w, we would get that from the previous answer of the same iteration. So the formula would still be the same, but the values would be different. So let me just copy this one. And put it right here. Now this would be our Gauss-Siedel's method. Now, as what I stated, the recently computed component values within the same iteration would be used. So for our x sub n plus 1, since we have not yet computed any other values right here, it would be 0. However, for our y sub n plus 1, the value of our x right here would not be 0. Instead, it would be 0.6. So let us change that for Gauss-Siedel's model. So, or M4, instead of M4, it would be this one. And then next, for our x sub n plus 1, just like our y sub n plus 1, the value of our x and y would proceed from the recently computed values. So instead of 0 and 0 for x and y, it would be the recently computed, which is 0.6 and 2.32727. So instead of m4 or x sub n right here, it would be this one. And our y would be the recently computed. Lastly, for our w, the same as what we did with the x, y, and z. Instead of y sub n right here, it would be the recently computed. So this would be right here. And our z would not be 0, but instead this one. So as you can see, we have our root right here. Comparing the two, the value of our roots is still the same. However, the number of iterations is different. So as you can see, in the Jacobi's method, there's more iterations. We got the same roots in the 16th iteration. However, for the Gauss-Siedel's method, we got the root in the 15th iteration. So we can say that in Gauss-Siedel's method, it is more quick, or it is quicker to solve for the roots, since you are immediately using the values of the recently computed x and y. That would be all. Thank you.